In this video, we're going to cover section 3.2 on polynomial functions and their graphs. In section 3.1, we focused on just second degree polynomials or quadratic functions. This section moves on to if the highest power of x is larger than 2, so degrees of 3 and higher. So the definition of a polynomial function looks like this. I know this notation is a little bit confusing to read, but all this really says is this a sub n is the coefficient of this term, x to the power of n. This is the coefficient of x to the one lower power, etc., until we get down to a constant term. So n is a non-negative integer, meaning it is not a negative number and it must be a whole number. So like 1, 2, 3, 4, 5, etc. And then the a sub n minus 1 are just real numbers that are the coefficients of these terms. So the most important thing that we're going to look at in order to start our graphing process is looking at the degree of the polynomial, which means the largest power of any variable, or n, and the leading coefficient, meaning the coefficient in front of that highest power term, a sub n. All right, so graphs of polynomial functions are always smooth, continuous curves. Once we start to put all the information together and connect the points, we're going to draw our graphs in nice, smooth, continuous curves. There's not going to be any gaps or breaks or holes in the graph like there could be like on a piecewise function or something. So that's important to remember. So the first thing that we have to look at to decide what our graph is going to be is what we call the leading coefficient test. So basically this is telling us what happens on the ends of the graph. It's predicting our end behavior. So in a polynomial function, as x increases or decreases without bound, the graph of the polynomial will eventually rise or fall. So on the ends, it's either going to go down on both ends, up on both ends, down and then up, or up and then down. So there's 4 cases. So to know which of those situations occurs, we look for the degree and check to see if that's even or odd. So an odd degree case here, even degree over here. And then the leading coefficient could be positive or negative. So in both the even case and the odd case, we'll talk about positive and negative leading coefficients. So under number 1, it says for n is odd, meaning that the degree is an odd number. If the leading coefficient is positive, a sub n greater than 0 means leading coefficient positive, the graph falls to the left and rises to the right. So it goes down on the left and up on the right. If the leading coefficient is negative, the graph rises to the left and falls to the right. So it's exactly the opposite. It would go up on the left, down on the right. So for an odd degree polynomial, the ends move in opposite directions. It's either down, up, or up, down. So the down, up is kind of like x cubed from our common functions out of section 2.5. And then up, down would be like negative x cubed if there was a reflection of that graph. So any odd degree positive coefficient looks like this on the ends, and any odd degree with a negative coefficient has this behavior on the ends. For the even degree case, the ends are going to point in the same direction. So if n is even, meaning that your degree is even, if the leading coefficient is positive, the graph rises to the left and rises to the right. So it's going to go up on both ends, like this one. If the leading coefficient is negative on an even degree, it's going to fall to the left and fall to the right, so point down on both ends as this one does. That models the same behavior as the common function x squared. If it's just f of x equals x squared, it goes up on both ends. That's an even degree polynomial with a positive coefficient. If there's a negative in front of x squared, it's going to turn it upside down and be even negative, which would model the down-down behavior. So the first few examples are just indicating end behavior. So for this polynomial function, we have a degree of 3 and a negative coefficient. So if the degree is an odd number, 3 is an odd number, coefficient being negative 1 is a negative number, so our end behavior would be for the odd degree negative case, which is rises on the left, falls to the right. For the next example, the coefficient is 11 and the degree is 4. So the degree is an even number and the coefficient is a positive number. So end behavior for an even degree positive coefficient is rises on the left, rises on the right. We should also be able to use that rule backwards. So if we're given a graph, determine if the polynomial has a positive or negative coefficient and if the degree is even or odd. So if this was the graph that we're given, we notice the end behavior being down, down, or falling on the left and falling on the right. So that would mean the degree would be an even number and the leading coefficient would be negative. In part B, it falls to the left and rises to the right. So that means opposite direction is always going to mean an odd degree. And down on the left, up on the right would mean a positive leading coefficient. The note says a polynomial function of degree n has at most n minus 1 turning points, meaning that in this function, if there has 1, 2, 3 turning points, it could have at most degree 4. At least degree 4, right? It has to be at least a 4th degree polynomial if it has 3 turning points. This one has 2 turning points. This would have to be at least a 3rd degree polynomial. That's another way that you can kind of tell if the degree is even or odd. You count the number of turning points, the minimum degree being 4 is an even number, and 2 turning points would mean add 1, and 3 would be your minimum degree, which is an odd number. All right, zeros and multiplicity is the next step, how to know what happens in between the ends. So a zero of a polynomial means a value of x for which f of x is equal to 0. Zeros are also sometimes called roots or solutions to the equation f of x equals 0. So a zero or a root or a solution, all those words mean the same thing. So if we're setting f of x equal to 0, that means setting y equal to 0, we're looking for x-intercepts. So any real solutions that we get by setting f of x equal to 0, we're going to see as x-intercepts on the graph. So a 0 means an x-intercept. Multiplicity of a 0 is something that we can look for that will tell us the behavior of the graph at the x-intercept. What does the graph actually look like? Does it look like x squared and just touch the graph, or does it look like x cubed and cross through the x-axis? So the multiplicity means the number of times the 0 occurs. In other words, it's the exponent attached to the factor. So if we have our function in factored form, each factor leads to a 0. The exponent on the factor indicates the multiplicity. So in this example, f of x equals negative x cubed times x minus 2 squared. That's the factored form of a polynomial. So if I take the factor x cubed, set it equal to 0, to solve for x, we would cube root both sides and get 0. So the x equals 0 is the 0. Its exponent was 3, so that means it has a multiplicity of 3. The second factor is the x minus 2. So if I said x minus 2 squared equal to 0, I would get x equals 2 as the solution, right? The value of x being 2 makes that true. So the exponent of 2 means that my multiplicity is 2. So if the multiplicity of the 0 is an odd number, that means the graph will cross the x-axis at the 0. So for this example, at x equals 0, we would see it crossing the x-axis because the multiplicity is an odd number. If the multiplicity of the 0 is even, then the graph touches the x-axis and turns around. So it basically just bounces off of the x-axis at the 0. So at x equals 2 on this graph, since the multiplicity is an even number, when I get to this x-intercept, it would bounce. It would touch and turn around. Regardless of whether the multiplicity is even or odd, graphs will tend to be a little bit flatter near the 0, the higher the multiplicity is. Okay? So we just talked about this one. This was again the one that we saw earlier. So this one gives me x equals 0. Its multiplicity is odd, so the graph will cross. This factor gives me x equals 2. Its multiplicity is an even number, so the graph will touch and turn around. So here's another couple examples of using that rule. In this example, this is also in factored form already. 4, that does not contain any variables with it. There's no x's attached to that 4, so that's not going to lead me to any solution. So I don't have to use this to find any of my zeros. So I only look for the factors that contain x. So this factor contains x. If I set x minus 3 equal to 0, I would get x equals 3. Its exponent is a 2, so that means its multiplicity is 2. That's an even number, so this graph will touch the x-axis and turn around at x equals 3, or bounce. This factor, x plus 6 set to 0, would lead to x equals negative 6. Its exponent would be a 1. If there's no exponent written, it is assumed to be a 1, so its multiplicity is 1. That's an odd number. So for odd multiplicities, the graph crosses the x-axis at that x value, negative 6. This next example is not given in factored form. So in order to utilize our multiplicity rules and find our zeros, we have to factor it. Okay, so if it's not given factored, you will need to factor. In this example, you would need to factor using the grouping method. That is something you should know how to do already. So to use the grouping method, we take the first 2 terms and put them in a group, and then we take the second 2 terms and put them in a group. So within the first group, we would factor out the common factor, which would be x squared, and that would leave x plus 5. In the second group, we would factor out negative 9, and that would also leave x plus 5. Grouping method only works when the leftover factor matches in each of those first 2 groups, which it does, x plus 5 and x plus 5, so we can factor out x plus 5 as a common factor. That would leave x squared minus 9 left over. X squared minus 9 is a difference of squares. It factors into x plus 3 and x minus 3. So my factored form is x plus 5, x plus 3, x minus 3. So this factor gives me the 0, x equals negative 5. Its power is 1, so that's the multiplicity. This factor leads to x equals negative 3. If it were set to 0, its power also 1, so that's its multiplicity. X minus 3 set equal to 0 gives x equals 3, and its power again is 1, so the multiplicity is again 1. All of these multiplicities are the same. They are odd numbers, which means the graph will cross the x-axis at all 3 of those zeros. All right, so how do we put all this together to actually draw a graph? Use the leading coefficient test to decide what the end behavior is going to be. Look at the degree and the leading coefficient to know if it falls on the left, rises on the right, whatever happens on the ends. Step 2, find the zeros and their multiplicities and use it to determine behavior at the zeros. So find all the x-intercepts and decide if it bounces or crosses the x-axis. Step 3, find the y-intercept. That is an easy step. It just means plug in 0 for x. So you might get an extra point to plot on your graph by doing that. Step 4, if necessary, find a few additional points. That's not always necessary, but you can always plot a few extra points if you feel you need them. And then sketch the graph using a smooth continuous curve. So our first example, f of x equals negative x to the 4th plus 4x squared. So our step 1 is our leading coefficient is negative 1 and our degree is 4. So it's an even degree negative coefficient, meaning in behavior would be down, down. Falls to the left, falls to the right. Finding our zeros and multiplicity requires it be in factored form. So if it's not factored, I have to factor it. So my first step of factoring this is to factor out the common factor x squared, and I'm also going to factor out the negative since this first term is negative. So I'm factoring out a negative x squared, leaving x squared minus 4. X squared minus 4 factors into x minus 2 and x plus 2. So this is my factored form. So setting this to 0 would lead to x equals 0. Multiplicity is the exponent 2. So that's going to mean it touches and turns around or bounces off the x-axis. X minus 2 set to 0 gives me x equals 2. Multiplicity is 1 because that's the exponent. And x plus 2 set to 0 would lead to x equals negative 2. Power here is also a 1. So these two factors each have a multiplicity of 1, means it's going to cross the x-axis at both negative 2 and positive 2. Y-intercept, remember, means plug in 0 for x. So if x were 0, both of these terms become 0, so we get 0, 0. Okay, so when we're starting to put the graph together, we're going to start with our end behavior that we said was down, down. So these little x's down here just means I know I'm going to start down here on the bottom quadrant. I'm going to end on the other side also at the bottom. Next, I would plot my zeros. So -2, and I put a little C just to remind myself I'm going to cross. 0, supposed to touch. That's what the T means. And then again at 2, it's going to cross again. My y-intercept happens to also be one of my x-intercepts, so I don't get any new points to plot from that, although sometimes you will have an additional point to plot by using the y-intercept. All right, so we're going to start down here on the bottom. Moving forward, we cross through here. We have to turn around, so a smooth continuous curve to turn around, touch or bounce off here, and then again you have to turn around and then eventually cross here and end up where you're supposed to end up. The graph should not touch or cross the x-axis anywhere other than the zeros that you have found. So that's how you know you're finished. You don't have to come back up and down again. The plotting additional points, if you wanted to plug in -1 and plot the y value and +1 and plot it just to get more accuracy there, that's fine, but it's not necessary. All right, our next example is given already factored. So our degree and leading coefficient test, we have to do a little bit more work here. So if there's a coefficient in front, we would write it down. Here it's a 1, so I don't need to write it. Take the highest power of x inside, raise it to the power outside. So this would be x to the first from that first factor times, and the next factor it's x to the third times, and then x to the first. So only worry about the highest powers inside of each parenthesis and multiply all these together. So x cubed times x to the fifth would, times x to the first would equal x to the fifth because we're adding powers, right? 1 plus 3 plus 1 is 5. So that tells me that if this were expanded out and not factored, the leading coefficient or the degree would be 5 and the leading coefficient would be a 1. So an odd degree, positive leading coefficient means my end behavior is down, up, or falls to the left, rises to the right. So I would have put the x's down and up. Step 2, find the zeros. Since it's already factored, that step is a little bit quicker. So I just set equal to 0 and solve. So I get -3, power of 1, so multiplicity is 1. Set this to 0 gives me -1, power is 3, so its multiplicity is a 3. I just put the word flatten because remember it said the higher the power, the flatter it will get. It's still going to cross because it's an odd number, but it's going to flatten out a little bit because it's larger than 1. And then setting this one gives me -4. Again, power is 1, so that's the multiplicity. All of these are odd, so it's going to cross the x-axis at each one of those. Y-intercept means plug in 0 for x. So if I just plug in 0 for all the x's, and simplify, this becomes 3, 1 cubed, and 4. So 1 cubed is 1, so that's 12. So it's going to cross the y-axis at 0, 12. So if I knew it was down, up already from my end behavior, my next step would be to plot my points. So at -4 right here, -3 is right here, and then -1 is right here. And then 12 on the y-axis is up here. So I would have started down in this bottom quadrant. My first intercept is -4. I cross. I got to quickly turn around and cross again at -3. And then come back here and notice how it kind of flattened out before it crossed at the -1 because it had a 3 as the multiplicity there. But it still crossed, and then I continue upward to make sure I cross my y-axis where I'm supposed to at 12, and then I just continue to move upward because I have to end up high. And that's it. All right, our last one here is working backwards. They give us a graph, and they are asking us to first find the zeros and decide if the multiplicity is even or odd. So remember, zeros means just look for the x-intercepts. So I have an x-intercept at -2, and then another one at 1. So at x equals -2 is my first zero. I notice the graph crosses the x-axis there, it goes all the way through it, so that's how I know that my multiplicity is odd. At 1, my x-intercept here, x equals 1, notice the graph bounces or just touches and turns around, so that means the multiplicity is going to be even. Part B says write an equation as a product of factors. All right, so my equation, just in factored form. I need a leading coefficient in the front. So because it's down, up, that would indicate a positive leading coefficient. So I'm going to use a positive 1 here. If it had been up, down, or down, down, we would have to put a negative 1 in the front. It tells you in the directions on this problem to use a positive 1 or a negative 1. Okay, so that's determined by BN behavior. All right, so negative 2 was a 0. So one of my factors is x plus 2. And its multiplicity was odd, so we're going to use a 1. It says use the lowest possible degree. So if it's odd, we use a 1. If it's even, we're going to use a 2. If you saw it do a flattening out like this, it would be a 3. So 1, 2, or 3 are the only numbers we're going to need. So x plus 2, and then just crossing straight through without flattening is an odd power of 1. X equals 1 means the factor is x minus 1, and then its multiplicity is even, which would mean the lowest possible even number would be a 2. So this would be my factored form. And then part C says find the y-intercept. So you should be able to, if this is correct, you should be able to plug in 0 into here and solve, or sometimes you can tell by looking at the graph, it looks like it's crossing here the y-axis at 2. If I plug 0 into my equation, I get 1 times 2, and then this would be negative 1 squared. So 1 times 2 times 1, 2. So that verifies that that is correct. All right, that's a fairly long section. There's a lot of new information in section 3.2, but that is the end of that section 3.2.